So one of the important things to understand about this instrument is that everything that has to do with either a control voltage for some aspect of a voice, or for measuring the value of the pots and buttons, well, the pots actually, they're all controlled by and measured by one single digital to analog converter, which also does double duty as part of a analog to digital converter. So the other thing what that means is that all of the control signals, all the control voltages, they're all time division multiplexed. So what that means then for those when you're doing the time division multiplexing, I'll show this later. It's actually a really neat thing to see is the output of the analog in signal that gets demultiplexed and sent to each of these boards. It looks like a bar graph basically, and with each of those bars is one of the control voltages. So what happens then is that's where these circuits here are important, and ones down here. Basically what they are is they're sample and hold circuits, so that when it comes time that the control voltage is present on the demultiplexed output, a sample is grabbed of it, it's held, and then that output is fed out, it's held and buffered and sent out as a control voltage to whatever part of one of these voice cards that it's destined for. So getting back to the tuning here with these tuning coefficients, the other thing that may be happening is that the sample and hold circuit, maybe there's something wrong. Each sample and hold circuit has two components to it. There's the CA3080E, which is a transconductance amplifier, and they use those they're actually used for the voltage controlled amplifiers and a bunch of other stuff in this instrument. The other part is this guy here, which is a JFET input op amp. It's a TLO72. So that's actually a dual op amp. So these two ICs in combination with this capacitor, resistor, and another capacitor and another resistor, that's the sample and hold circuit. So that's another spot where we could have problems. If that sample and hold isn't functioning correctly, then perhaps we're going to get skewed voltages, like in this case where the tuning coefficient is a bit too high. Taking a step back, you can't really see them so well here, but each of these is a capacitor, and that's the capacitor that stores the charge from when the demultiplexed output, when that voltage is sampled, there's one of these capacitors for each sample and hold circuit. So it could be that one of these capacitors, in this case for channel 2, I think it's this one. If one of those capacitors, if its value is off, or the capacitor is starting to degrade, because this machine is 30 years old by this point, and components start to degrade over time, particularly capacitors. So it's possible that one of those is going, maybe one of these is going. Point being, if there's something wrong with the sample and hold circuit, then that could affect the tuning. It could also affect any number of the other control voltages for a voice. And this is where we have these other sample and hold circuits for various other control voltages. So it could be that the control voltage for the frequency of the oscillator 1 or 2 on this voice is off. But the thing that I find interesting about this, though, and leads me to believe that that's not the case, is that both oscillators are mistuned. It's not like one is perfectly tuned and the other one is just screwy. They're both wrong. So what I get from that is that would imply that it's probably this KCV2, which is this sample and hold here. If it's off, then that one control voltage, which is the control voltage from the keyboard, controls both oscillators. So I suspect that the problem is actually in this sample and hold circuit for KCV2. Now, what I can do, similar to what I did with switching the voice cards, these two ICs are socketed. So what I can do is take the two ICs for sample and hold 2, and beside them here is the sample and hold for voice 5. So I could swap these 4 ICs and see how things function at that point. Now again, if things continue to malfunction, then I can be fairly certain that it's not a failed component for either of these amplifier ICs, and it may be something else, whether it's a capacitor, a resistor, or something else further along the chain. Now we were looking at the circuit board there. Here's the section of the schematic that corresponds to that. So here's our analog input. This is the time division multiplexed control voltage signal, and you can see there's numerous demultiplexer chips on this board because there's a whole bunch of control voltages, and each of them need to come from someplace. And each one of these demultiplexers only has 8 outputs on it. So this one here happens to be the one that controls the keyboard control voltages. So you can see they're key CV1, key CV2, 3, 4, 5, 6, 7, and 8. So it's this one here that I'm interested in. So you can see there's a 0.022 microfarad capacitor. That's that polyester, the silver polyester capacitor. There was a bank of 8 of them tucked underneath the processor board. That's what each of those are. So that's what stores the charge, or the voltage that's sampled from this demultiplexed output. Because what happens is, what the demultiplexer does is it takes this input voltage and sends it to one of these outputs at any given time based on these control signals here. So we've got A, B, C, and this enable pin. So what's going to happen then is, at some point when we're sending the control voltage for key CV2 here, we'll set these control pins accordingly. There's going to be a voltage here, and when it comes time that the voltage at the multiplexed output is actually for this one, then this enable pin will be high. The selection pins will be set accordingly, and the signal coming in here will go out here on this KCV2 output. That pops over to here. It charges this capacitor, and then we have a buffer amp, which is a very high impedance op amp. And the idea why it's important to have a high input impedance is so that when this is measuring the voltage across that capacitor, it's not draining very much of the charge, very little amount of charge off of it. So little that basically the next time that this control voltage is sent out to KCV2, it charges that capacitor again. So it doesn't really get a chance to discharge the capacitor at all, because it's a high impedance input, so it's not draining very much of the charge off at all. And it's a non-inverting op amp here. So that output goes out to here. This is the transimpedance amplifier. The output of it is buffered, and it is going into the second half of this op amp, which is the TLO72. In this case, it's an inverting amplifier. And then we can see we've got a feedback channel here going back to the inverting input on this op amp. So anyway, what this is doing, that's the sample and hold, and gives us this key CV2 control voltage. So this is, like I said, this is what I'm going to look at next, and I'm going to swap these two components with the ones for key CV5. So what I've done here is I've swapped the ICs for a sample and hold circuit for voice 2 with that for voice 5, and this is the keyboard control voltage sample and hold. So the idea being, we don't even use the sample and hold for 5, 6, 7, and 8. So what is likely to happen then is, if either of these had problems, and the other assumption is that both of these are good, then what happens then is, by swapping them, then we would have 2 good ICs in this spot and 1 or more flaky ones here. So what should happen is, if that is in fact the problem, when I power this back up and tune it, we should hear that voice 2 sounds proper. So let's give it a try. Hit the tuning, and here we go. Look at that. Now I'm just going to turn it off again because we can't hear voice 1. I'll turn it again. So that was the problem. It was one of those ICs. My guess is that of the two, the one that I think is most likely to fail is this TLO72. The reason being is that is a JFET input op-amp. So field effect transistors, they're a bit more finicky when it comes to being sensitive to electrostatic discharge, or the sort of stuff that can damage a component. So if one of those op-amps has been damaged, then because both halves of this are used by the front and back end of the sample and hold, then the entire circuit's not going to function properly. This other one, this 3080E, the trans impedance amplifier, I'm not sure if it uses CMOS components or field effect transistors at all, or what. But so what I'll do next is to further narrow down the cause, I'm going to swap these two guys back and see if the problem is back again. If it's not, then it's one of these two. Either way, voice 2 is working properly now, and it had to do with this sample and hold circuit, which is good news because we understand now what was causing the problem, and not only that, we've fixed the problem. So what we see on the scope now is I've captured the same signal set as I did before when things were malfunctioning, but this time we can see that although the control voltages are slightly different, the frequencies are very, very close. They're right around 65 Hertz. And if we listen to all these voices in unison, they're all in tune. And if I hit the tune button, now if I take it out of unison, this one, it's a little bit cranky right now. It needs to be screwed down properly again. So as I said earlier, my final step is to swap these. I'm going to swap first the TLO72s between sample and hold for voice 2 and 6. I think that's actually the component that's failed, but I need to confirm that. And if that's not the cause, then it's that CA3080E. Either way, that's the final step, and that will get me to the point where I have identified the root cause of the problem.